Hello, all. So we're building towards being able to prove trig identities. And so far this semester, we've talked about plenty of identities. We've learned the definition or the way we orient our trig identities with regard to a right triangle. So an acute right triangle, we've got our SOHCAHTOA and then the reciprocal identities. So basic identities, we've got these reciprocals. We also know that tangent is sine over cosine. We have a Pythagorean identity and two other versions of it. And of course, we can rearrange all of these. We also know even and odd properties. Sine and tangent are odd, where cosine is even. And we've learned some newer identities here, our double angle and our sum and difference. As you start thinking about what of these new identities you really need to know, we're going to make sure we know Pythagorean, double angle, and the sum or difference. We know those. We have those stored in our brain for use when we need them. We've also talked about these half angle identities. These I don't personally think you need stored, and if I do give them to you on the test, you're not going to need to know it. So I don't like to say not on test so much anymore, but you don't need to know it on the test. So I might say, hey, use this half angle identity to find the exact value of some angle on that could be found on the unit circle, but is not one of the values we know on the unit circle. And just to fill out my nice piece of paper chart here, we also know how to convert between radians and degrees, and then we will talk about law of sines and law of cosines coming up. So in section 7.3, we talk about proving trig identities. So we are going to take a statement and rearrange one side or the other, not moving terms from either side, to try and show that both of the sides are equal to each other. So we have two strategies. We start on the left or the right. And the one strategy, which I'll try to do when we work through these proofs in our notes, will be to work on only one side. So work on one side and try and turn it into the other. And then as you become more comfortable proving, then I say, let's move towards maybe working on both sides. We manipulate both sides independently until they are equal. We do not move terms. We never move terms from one side of the equation to the other. So you're not going to say, oh, there's a plus 3x. I'm going to subtract 3x from both sides. We don't ever want to do that. Okay, and we have some hints. So we've addressed using all of these tools so far. So we'll use either one of these two methods above, start on the left or the right, working only on one side, or we can work on each side. So one thing that's helpful is to pick the more complex side and to start there. So to simplify something that's really ugly looking is much easier than if it was just, say, just sine of theta. So we'll pick the harder side. Carry out any algebraic manipulations, which is factoring, multiplying, distributing, adding and subtracting fractions. Especially helpful when we are dealing with fractions. One thing that we like to do would be to multiply by 1 because that's going to give us a common denominator, so I could add or subtract some fractions. We've also mentioned that it can be really helpful to convert everything into sine or cosine. So secant, tangent, cotangent, cosecant, turning those into sine and cosine. So we only have two trig functions to deal with. And lastly, this is my favorite. Put your pencil on your paper, try something, and be amazed. So let's do our first example. Here we have an identity. We're going to show that this is true. So as I said, we can work on both sides, but I think it's helpful for us as students when we're learning to think about only working on one side. So I like to create a wall, and just remember, you never move things across the wall, right? So there's a huge wall and things never cross. So now we look at the left and we look at the right, and we have to pick a side to work on. So here I do see a double angle substitution, and I know the value of sine 2 theta. But on the right, I see that there's an algebraic manipulation that I can apply. So I'm going to FOIL. I have sine of theta plus cosine of theta times sine of theta plus cosine of theta. Foiling this, I'm going to get sine squared theta plus 2 of sine theta cosine theta plus cosine squared theta. If you have a hard time foiling, you might want to take that s plus c and write it like this, sine plus cosine, and that might help you. So first we have sine squared inner, that's a sine times a cosine, outer, again a sine times a cosine, and the last two would be cosine squared. So you can see we have 2 sine times cosines. So just to help when you think about foiling that. Okay, so now looking at what we have, we say, well, do we have any identities? And of course, using the Pythagorean identity, we know that sine squared plus cosine squared we know that's equal to 1. So I'm going to sub that in. And now I have 1 plus 2 sine theta times cosine theta. And I should recognize that 2 sine theta cosine theta is an identity. That is my double angle identity. And we know that that is equal to sine of 2 theta. So I have 1 plus, I'll substitute that in and I'll write it correctly. 1 plus 2 sine theta cosine theta is sine of 2 theta. At this point, we notice the left side is exactly equal to the right side, and we're done. And I write this symbol at the bottom of my proofs. It means therefore. So we can say this is true, we are done. And that's how you prove. So in the videos that follow this, I'm going to do a lot more proofs. And as long as you remember all of these strategies and your logic for proving, you're going to be good to go. So make sure you know these hints and determine whether or not you're going to work on either just one side or both sides. But you do want to recall that when we are proving or verifying identities, that we never, ever, ever are moving terms from one side of the equation to the other. That's an equation solving property that we use, and that's not what we're doing yet. All right, so that's your first proof. Come back, we'll do some more.